Hello and welcome to today's webinar, How to Monitor and Size Workloads on AWS i3 Instances. I'm Julia Angel, Marketing Director here at ScyllaDB. If you have questions for our presenters or technical issues with the webinar, please use the chat window located in the lower left corner of the console. The recording, the deck, and links to resources will be sent to you after the broadcast. Now I'd like to go ahead and introduce my colleagues, Ayel Gutkind and Glover Costa. Ayel is a solution architect at ScyllaDB. Prior to Scylla, he held product management roles at Mirantis and DataStax. Before that, he spent 12 years with Mellon Technologies in various engineering management and product marketing roles. Glover Costa has been in charge of i3 support and Scylla's I/O subsystem and has over 10 years of experience in low-level software like the Linux kernel. And with that, I'm going to hand it over to the presenters. So Ayel, please take it away.
Thank you, Julia. Thank you, everybody, for joining us. Let's go in. So we will cover who we are, what we do, and who uses Scylla today. We're going to explain how to start and get Scylla working for you. We're going to explain the monitoring solution that we have, a little bit about data modeling and the impact on operations, how Scylla is compatible with current existing solutions, and we will finish with a short Q&A. So what we do, Scylla provides you with the same capabilities and high availability solutions as Cassandra. It scales, it provides you a very flexible replication and multi-data center capabilities. However, it is totally different in terms of the performance it provides you. We can do more than 1 million IOPS or operations per second on a single node. More than that, our latency on the 99th percentile is extremely low. We auto-tune Scylla to take advantage of every part of your server. So if you have more memory, if you have more CPU, you have more disk bandwidth, Scylla will take advantage of it. Scylla is an open source project, and you can basically go on our GitHub and contribute to the source itself. We are piggybacking on the Cassandra community, meaning that we can support the same third-party tools that exist today in that community. For example, you can do analytics with Spark and Presto, time series databases, as well as graph databases too. Scylla is deployed at several ad tech companies, infrastructure solutions, social media, as well as DBaaS solutions that are offering on our website. So please take a look at those logos and take a look at those DBaaS solutions that you can log in and use Scylla. Looking at benchmarks is sometimes a little bit, you get a cynical view of it. However, in this case, the guys who made this benchmark are Samsung Memory Solutions, and they tested Scylla versus Cassandra. What they found out using YCSB benchmark, which is a dominant benchmarking solution out there, is that Scylla can provide you between 10 and 20 times better performance on the same workload, on the same hardware with the same capabilities. So you can actually provide more resources to your customers, or your application can sustain more users with the same system you're using today. So let's go into more details on how we monitor and understand the bottlenecks on your deployment. So installing monitoring solutions with Scylla is fairly easy. There are two options. The first one is the clean and simple, we call it. You're using Docker-based Prometheus and Grafana. So it's very intuitive one. You go in, you do a pull from our Git, and you install two containers. One is Prometheus, and the other one is Grafana. You configure the Prometheus and Grafana to look at the Scylla nodes, and we will show you exactly how you see it on your screen. The other option is, if you already have a Prometheus and or Grafana solution, you can use our configuration files, the YAML files, the INI files, and the JSON files to basically promote the information from the Scylla servers into your own installation of Prometheus and Grafana. So let's see how it looks like. So basically, you're going to get a Grafana-based interface with Scylla information on it, and we will go into details into each one of them. So Glover, what happens if I want to change something here?
Yeah, so we have in the next slide one example of something that we have used recently. Those dashboards are provided for your convenience, and they contain the information that we usually consider to be the most important for the general case. But you can just configure it, and you can change the dashboards and add things that are specific to your deployment. That's easy to do.
Great. So how about we set up some monitoring?
Sure, let's do that. We need to fire up a terminal here.
So I'm going to share my terminal screen. Bear with us a minute. Great.
Okay. Yeah. So the first thing that we need to do, we'll clone the repo. We're going to be using the first method that. First, let's look at the servers before we actually load up the monitoring. And we need to get the IP addresses of the servers. Yeah. And you can see that those instances are the i3 16x large. They have 32 cores. And we have the IP addresses in there. You can see them. And now we're going to actually fire up the monitor with those addresses. So as I said, we're going to be using the first method that Eyal described, which is our git tree containing all the standard dashboards, and everything can be set up with a simple script. So we're going to create a directory for our experiments today. Let's switch into it. Okay. And inside that directory, we're going to just clone the tree. That's done. And now we have a script. You don't have to use it. You can configure the files manually with the addresses of the servers. But that script will generate the YAML files that you need to use. So if you take a look at this directory, Scylla nodes, that's the -d option. You're going to see the two files that we need to configure our monitoring solution, Scylla servers and node exporter servers.yaml. Now all we have to do is start. So there is a script. Start all, and we are specifying that we are using version 1.7. We are pointing the monitoring solution to those files we have just created. So let's just do it. That's great. Now, if we go to the browser now, port 3000, and load, we'll see the Grafana is just running. And we have a couple of dashboards that comes by default. You can see the cluster metrics, the per server metrics, IO metrics, and we can see our 3 servers in there. Yeah. When we run the workloads later, we will explain a little bit more about what those graphs are. At this point, let's just go back to the presentation, Eyal.
Thank you, Glover. So on our next slide, we will cover why we want to use the AWS i3 instances and Scylla, and what's the mess that we see here. So if you think about the i3 instances, those are very, very powerful machines you can get into your usage. Those go up to 64 vCPUs, 488 gigabytes of RAM, and 15.2 terabytes of NVMe SSDs. This is a very, very powerful machine. And there is huge benefits of using such a powerful machine with Scylla. Since Scylla can take advantage of all those cores and basically create what we call a shard per core. So every core will take a chunk of your data and going to be responsible for that specific chunk of data and provide the most performance solution to create both queries as well as responding to your requests from the database. If you look on other solutions, basically what's going to happen is that usage of that CPU is opportunistic. So in sometimes what's going to happen is multiple shards or multiple threads will try to use the same CPU or the same vCPUs in this case and basically clog each other or lock it. At that point, you will have some cores that are completely idle, while others are basically oversubscribed and create bottlenecks. And at that point, you will see stalls in your data movement in and out of the database. Scylla does not suffer from that perspective since we are using a shard per core. So if you have a very powerful machines, you will have a lot of shards, and at that point, you will be able to support multiple applications and multiple users at the same time. If we're looking in terms of memory performance on those instances, you will see that 488 gigabytes of RAM provides you a very well way to cache information. So Scylla, one of its biggest benefits is a unified cache. If you look at Cassandra today, basically you have two different caches. One is the key cache, and the other one is the raw cache. And it's, let's say, it's a black magic to tune it correctly for both on-heap and off-heap for both of them. Scylla uses a unified cache, meaning that everything, both the keys as well as the rows, are cached in one place. More than that, we have a very, very efficient way to store those that information in the cache. Since an SS table page is 4 kilobytes, every time you're going to read any data that you have in your SS tables, you're going to have to read a full block. This is how Cassandra works. However, with Scylla, it's a little bit different. Scylla will take just one portion, just the data that you need, and cache it and bring it into our memory. At that point, basically, you don't have any more parasitic rows. Saves you, in this case that we have shown here, over 3.5 kilobytes of RAM. So there's going to be less evictions from the cache and more useful and hot cache you're going to be using. In addition, any time that, for example, Cassandra has to go and fetch information, basically it's going to lock that specific thread. It's because it's a page fault. Go to the IO subsystem and fetch the information. So every time you have an eviction or a retrieval of a new block, it's a stoppage in system. At that point, again, you're going to suffer from higher latencies and lower throughput at the end of the day. So how about we show the CPU and memory workload on a monitor?
Sure, let's do that. So what I'll be running here today, we're going to go back to the terminal. And that's the Fedora terminal, the first one. Yeah, let's do that. It's a very simple schema with a key value. So the keys, it's a key value schema. Both the keys and the values are fairly small. And let's just start it. Yeah. It takes a while to start, and we're just going to wait for it in the dashboard. Very soon we're going to see the load coming. Because this is a load that has fairly small keys and fairly small values, that's going to be exercising a lot of the CPU and not a lot of the disk. Later on, I'm going to show you an example in which we're going to be exercising a lot of the disk, not too much of the CPU. So we can see that those instances will scale no matter what is the resource that we need. So we can see we're almost there. The load should be starting. Yeah, here it comes. I think it's refreshing at every 30 seconds. Let's just show them how we do that once we're here. We can see that we can, if we go in the interface, it's set to refresh every 30 seconds. We can just move it to a 5-minute window. Yeah, it's going to be easier to see and refresh, let's say, every 5 seconds. Refreshing on the left, and then, yeah, every 5 seconds. Exactly, and it's going to be easier for us to see. This load's not going to run for a long time, okay? And we'll just see how it performs. How many operations a second can you do?
Wow. Glover, could we look at Linux metrics, for example, like stop?
Yeah, sure. A lot of people do that, and as a matter of fact, it's the most intuitive way because it's something that you already used to do. So what we need to do is, let's just do this. Let's go to this terminal, to the other one, CentOS, and from this go back to the Fedora terminal. And at this point, we can
just run top.
No, we need to log into the server. This is one of the servers we saw earlier when we set the monitor. We got the addresses. And let's just do top, and then press 1. With 1, we're going to see the per CPU. And what do we see there?
Everything is clogged.
Everything is clogged. I mean, it looks really clogged. And the way we don't recommend people look into this is that Scylla, one of the architectural innovations that we have in Scylla, and that we bring into the database world, is that it's very frequent in the high-performance computing industry, is that we don't really do interrupts. We do busy waiting for new requests. So when we process your requests, we just keep busy waiting until the next request comes in. So you're going to see your CPUs at 100%. But if at this point we go back to the Grafana dashboard, all right, let's go there. You can see that the load per server is actually not that high. So it is about 40% real load, actual load. So when we're monitoring Scylla, we highly recommend that we look at this load from this perspective. That is the load per server. That is the real load of the cluster, without taking into account all the busy waiting, all the pooling that the server is doing. We have another example. We can probably just cancel this one. It's going to run for a couple of minutes at most anyway, but we can just Control-C in the Fedora terminal. Yeah. And now what we're going to do is we're going to run a very similar workload. It is exactly the same schema. Everything is the same, but we're going to run more threads and more load. Here we go. So let's see what happens.
I'm just going to show the top again here. See that it's basically come down. So we stop the workload, as we see here on the Grafana one as well.
Yeah, we're going to see the difference. So let's look again. Some more information about this workload. I mean, those workloads that we're running here, of course, they are synthetic workloads. They're going to run for a short period of time. This one has a replication factor of 1. So it's really like a tree cluster with, in which each of the nodes in the cluster is getting a piece of the data. Oh yeah, and an important information I forgot to tell you, you could see some nodes going down. It's actually restarting the processes between the runs. But you can see now that let's look at the request served per server. And we're going to see that each of the servers is running more than 1 million operations per second. So the 3 servers altogether, you can see in the total requests at the top, they're running 3 million operations. Again, it's a replication factor of 1. If we go down, we can see the network and the disks. Yeah, so this is a single disk. What we're running here is actually a RAID array. If we go to the top, let's show them how to do this. You can pick which disk you are monitoring. So MD0 is actually the RAID array. We're going to look at it, and you can see that it's running around 250 megabytes a second. Not that impressive, but as I said, this is a workload that is stressing the CPU. Let's go back.
You want to see the network?
Yeah, the network. It's also not extremely loaded. This machine can do around 20 gigabits a second. What the real load is here, it is around 80%. That means that this CPU can actually take more than this. I mean, from the CPU perspective, we can actually do more, but we will stop at this point. And this is if you at some point, I mean, when you get to 100%, your latencies are hurt by a little bit. But you can see that at this level, at this threshold level, around 80%, we're running 1 million operations per second in in a single server. It is a 32 CPU, 32 core, 64 virtual CPU server, but it's running this load. Let's go back to the presentation.
Thank you, Glover. Great. So as Glover showed us, basically we have a very performant machine. But as we saw in the last two workloads, we have a very performant system underneath it in the SSDs. And we love SSDs. And the reason is we have a very good way to understand how the I/O profile looks on your machine. And how we do it. Basically, we profile the maximum concurrency you can have on a volume. In this case, we have a RAID 0 setup. So we will basically check every number of concurrent processes we can put on that specific I/O and measure the throughput and the latency. We will take it onto the maximum possible concurrency at the maximum throughput at the lowest latency. That guarantees that every request Scylla is going to put into the system will be answered the fastest while almost not compromising anything on the throughput. For example, in every database like Cassandra and Scylla, there are three major processes you're going to have. One is the query, the actual reads that you get from the database. Another one is the commit log. Basically, again, you are committing information into the data. And the last one is compaction. It's a backend process that helps you sustain a reasonable disk space on your machine. Compaction is a backend process. You don't want that process to hog your system I/O. So you will provide a queue that you're going to monitor the queue and understand how much of that queue you are allowing the compaction process to take, while not hogging the more truly user-face queries that come to your database. That allow us to provide a very consistent latency as well as throughput to the user. So we monitor every I/O that happens into the disk itself. Okay, can we show some I/O workload on this machine?
Yes, absolutely. We have another script prepared for that. The workload that we're going to be running this time, so let's go back to the terminal. The workload that we're going to be running this time is a replication factor of 3, so it's a more challenging workload. And quorum writes. So the previous workload has had a replication factor of 1, and then of course the consistency level, it's only 1, it can only be 1. But now, not only we're changing the replication factor, we're changing it into a bigger consistency level, we are also increasing the size of the payload significantly. Before, we were writing a couple of dozens of bytes. Now we are writing something in the order of 200K. It's considered like a fairly large blob for a database like Scylla or Cassandra. We can do a lot more than that, but that will be enough for today. And we just need for it to start. How about we just go directly to the disk?
That's good.
Yeah.
Here we go.
It seems like it's starting, right?
Yeah, it's picking up. Whoa, 1.5 gigabytes. But that's, yeah. But, you know, this bandwidth is nice, yeah, but it doesn't really sound impressive. Aren't those disks supposed to be a little bit more fast than just what we see here?
That's actually a fairly good speed for one disk, but this machine has 8 NVMe's in the RAID array, so definitely we should be seeing more than that. And I'll explain to you what's going on. First of all, let's look at the network. So we have metrics for the network a little bit below. And we'll see that the bandwidth for the network, I mean, it's pretty close to its bottleneck. Both the receiver and the transmission, if you sum them up together, they're pretty close to 2.5 gigabytes a second, which is close to the line rate of 20 gigabits a second. So at this point, we are getting stuff from the network, and the network is the bottleneck. Even though as you can see, we're actually using all the network. The card can do 20 gigabits a second, and so can we. But there is another factor that needs to be factored in here. So the load ended, and this load is basically only exercising the commit log. And to see that, I would recommend that we go to our other dashboard in which we show the classes that Eyal just mentioned. Exactly. And not only, yeah, we can ignore this or save.
I ignore it.
If and let's do the same thing for the same settings for this dashboard, just to move to a 5-minute. Yeah. 5 seconds, and then the last 5 minutes, and move the disk as well because it's still showing a single disk on the top. Let's just, yeah. And now we can see the RAID. And what this dashboard is going to show you is the breakout of the actual, on the top, like we're seeing now, we see the disk bandwidth. But if you keep going down, you're going to see the compactions bandwidth. You see that this workload is not generating any compactions. There are no queries. Mem tables are not being flushed. So all that bandwidth actually comes from the commit log, which is a process in which the network is involved heavily. You're still receiving our requests. So what we're going to do now, we're going to flush in a larger workload that runs for more time. Of course, those mem table flushes would happen naturally. They would take a long time to happen in the webinar here, so we're actually just forcing them. Let's force a flush and see what happens.
Is it going to be ugly?
No, it's not going to be ugly.
Okay.
So we're forcing the flush on the 3 nodes. Ansible is doing that for us. And we were successful. And with a little bit of delay, we're actually, if we pay attention to the mem table flush graph, as soon as it refreshes, we'll see the disk bandwidth. Yeah, there you go. So now you can see how fast we could actually flush that data. And why is that? Because the bandwidth that we got, let's just hover the mouse and see, yeah, around 6 or 7 gigabytes a second. And if we go back to the disk on top, we're going to see that now we're actually using all of that between, yeah, around 6 gigabytes, and that's all mem table flushes. Now, how about we just run the load again? Exactly. And when it finishes, we're going to flush it again and then force a compaction. And then we'll see how can we use like this for mem tables and compactions, and how fast those disks can go. That's going to take around 2 minutes. So yeah, how about we go back to the presentation? We can tell them a little bit more about what we do, and then we'll come back to see the results.
Definitely. So as we saw before, basically it's a powerful software for a powerful instance. We can take advantage of both the CPU, the memory, the SSDs. Every chunk that you have in your system, Scylla will take advantage of it. And that's exactly what Scylla brings into the table. So it's a fully utilization of your system. It provides you more bang for the buck because we know that those instances are expensive for your operations and you actually want to use them in a more efficient way. And that's exactly how Scylla is operating for you. Okay, let's see if, how it goes on our system. We will talk later on how and when we think that you should use the i3 instances. Okay.
Let's refresh it and see.
Let's see it's refreshing.
Yeah. So the load is just starting again, and it's the same load that ran before, and it's going to run for around a minute. Okay. Yeah, I'll just take some time to explain then that, as you can see here, there are 2 kinds of metrics. There are some metrics that are coming from Scylla. Example of those metrics: total requests, load per server, requests served per server. Those metrics are all coming directly from Scylla. The disk activity, it's coming from Linux. So there is something called Node Exporter that runs together with Scylla in the same node and will export metrics about the Linux host. Now the load just finished, and we're going to do the same thing again. Yeah. Ready? Yes. Awesome. And after that, we're going to compact it. There comes our flush again. So as we saw, when the commit log is running alone, it cannot actually drive the disk to its full speed. But in a normal system that is running for a long time, all of those things would be happening at the same time. Okay. Now, Ansible is going to help us again here to call a compaction in all of the nodes. That's the key space that we are using for this demo, the replication factor 3. And here it comes. Look at the bandwidth.
8 gigabytes.
8 gigabytes a second. Now, that's great. So one of the things that a lot of people are always asking us is, how can Scylla just be a lot faster just by switching the language? And some of the things that we talked about today should make it very clear. It's not only a language switch, but it's also a different architecture that allows us to use every resource in a very efficient way, even your disks. So if you have extremely parallel fast disks, Scylla can just drive them to the maximum. And even if you have like mem table flushes, compactions, all of those processes, they are extremely fast because you can basically use the disk to its maximum capacity.
Perfect. All right. Let's go back to our presentation. So when to use the i3 instances? If you look at the i3 instances, you will understand that AWS is pushing those into the market. You'll see the price points, you see the capacities that you can get from a single instance, and you will learn that it's the right instance for you. It has the most innovative networking networking infrastructure inside of it. It has a great CPU offering, and as I said before, memory and disk. So if you have a workload that requires I/O, if you see problems in your database that is halting on compactions, if you see that your CPU is being clogged because you cannot put more requests per second from your client, i3 instance together with Scylla will serve the metric that you need to provide.
There are other instances on Amazon that provide the same number of CPU, but none of them provides disks that fast. And when Yao said that those machines can have a lot of storage, those in particular, the i3 16X large, they have 15 terabytes of attached storage, and Scylla can make use of it all.
Great. Let's talk a little bit about data modeling. In many cases, we see our users trying to run a workload and they got stuck. What we find out in many cases that they cannot provide a very good sharding capacity for our database. In many cases, you will see, for example, that there is not enough entropy into the primary key. To add primary key, to get a primary key that is partitioned correctly and more evenly across our shards, what we ask you to do is provide a very granular way to cut the partitions into the shards. As we explained before, every partition space or part of the partition will be attached to a shard. So if you can create a very, I would say, homogeneously distributed partition for the primary key, it will help us provide you with the performance. So what's going to happen is every request you're going to send will go to a different shard or core in the system. That's a very way to create a database and provide that entropy. Another thing we want to look at is partition sizes. In many cases, we see huge partition size. That's basic. It's going to harm your ability to store the information in memory. Since those big partitions create a very inefficient caching, we create a very high transactions on the cache, creating evictions and insertions into the cache, which again will lower your performance. Let's talk about Scylla compatibility. So Scylla, as we said before, is compatible with Cassandra. We use the same SS table format. We use the same configuration file. So if you have a Cassandra YAML file, that YAML file will fit exactly as it is for Scylla. The CQL language, it's the same CQL language you're using today for your application, will be accepted by Scylla. It means no learning curve for your developer. It means no application porting from your current usage of the application. We use the same JMX management protocol. So if you have tools that somehow use those management protocols, you can still use them with Scylla. we use the same no-tool command. As you saw before, we will create the same output as you would get from the current existing Cassandra. Into using a third-party solutions, we are going to work the same connectors as you have today for Spark, Presto, and Kairos DB to get data in and out of Scylla. The new Janus graph, the next evolution of Titan, will use the same protocol both with Scylla and Cassandra, so you can move your application back to us.
And I think with that, we can take some questions, right?
All right. So the first one we see here is, can you clarify the JMX difference between Scylla Prometheus and Grafana and the one that comes with Cassandra?
Sure, yeah, I'll take this one. So we wanna have full compatibility with Cassandra, including for people who are already monitoring Cassandra using their monitoring stack or their own monitoring stack. Some people do deploy that. With Cassandra, that happens through JMX, and we do export some metrics through JMX with a connector. So we have a connector called ScyllaJMX that exports some of the metrics, but for native Scylla deployments, we do recommend using Prometheus, the method that we show right now. It has a lot more metrics and a lot more Scylla-specific things. The JMX is basically for things that already that exist as well in Cassandra.
All right. The next one we had is, could you talk a little bit about your workload, the number of partitions, size of partition, etc.?
Yeah, sure. So as we said, those workloads are synthetic. They're just for the webinar. Usually a normal workload will run for 4 hours to begin with. This one in particular, we had 2 different workloads. The first one wanted to exercise the CPU, and it was a simple key value storage, again with 1 key, 1 value, and they were fairly small, around a little bit less than 100 bytes. And the only thing that we changed when we got to 1 million operations per second per server was the number of threads, the number of loader clients, but it was still the same thing. For the second one, we basically moved to a larger payload, so it was still a key value, 1 key, 1 value, but the values now were larger, around 256K in size.
All right. So another one is, what is the difference between I2 and I3 instances? And this question is great because until now I used mostly the I2 instances, and they also have great CPUs. They have some SSDs in them, and okay, why should I use I3 then?
Yeah, I mean, I think Amazon is making pretty clear that I3 are the machines that we should be using from now on. And the way you can see this is because they have better hardware, and yet they're cheaper. So they're actually not charging you a premium for better hardware. On the other way around, you're paying less price. So you actually, if you want to use I2, you're gonna pay more money. It's more dollars for a machine that doesn't provide the same level of performance. So the number of CPUs is about the same, with the difference that I3 instances have 1 more class, the 16x, and I2 will stop at 8x. And the I2 instances have SSDs, while the I3 instances have NVMe devices. And you have more storage, faster disks, and if you can even get more CPUs with the 16x large, all of that for less money, less dollars than the I2.
Great. Those are the questions that I see for now.
So I don't see any more questions. Thanks everybody for joining us, and we'll have another webinar soon.
Thank you, everybody. Bye-bye.